So therefore this much region is called the depletion region or transition region or space charge region. But please bear in mind that this depletion region is not the result of a discrete process. It does not happen suddenly. There is a continuous process. Means first of all the nearby free carriers will combine with each other. Then this effect will go to the bulk side. Then more electron holes will combine with each other, and slowly this depletion region will get widened. But and this is now some time has been elapsed, some time has been spent in this, and still the depletion region is widening because this hole may combine with this may combine with this, so this may happen. But as this process is happening in the background, one more thing is happening to this depletion region, which is void of free carriers. Why it is void of free carriers? Because they have provided their free carriers. Now within this depletion region there is nobody to conduct the electricity. There is nobody to conduct the conduction current. Means a conduction current can only flow either with the free hole or with the free electron. So there is no electron and hole within this depletion region. So therefore it is called depleted of free carriers. So within this region there is no free electron or hole, but they have left behind their immobile ions, and because of them there will be created an electric field from positively charged scenario to the negatively charged region. So if you see, this in totality is a positive charge scenario from this to this, and similarly from this to this is basically a negatively charged scenario, and both total amount of that negative charge will be same as the total amount of that positive charge, because it is very simple, because one electron has combined with one hole, so therefore one immobile ion here corresponds to the same or opposite immobile ions to that side. So therefore if you count 8 number of immobile ions negatively on this side are same in amount, means 8 number of immobile ions, positive ions to that side. And please do not go by the numbers. For a clear understanding I am showing very small numbers, otherwise the same phenomena is happening with a very wide numbers, with very large numbers like some 10 to the power 14 or 15 numbers of free carriers. So with those many immobile ions the same thing is happening, but for simple drawing, for simple understanding, we cannot draw those many atoms or ions. So therefore I have only made some 8 or 8 so that we can simply count it. And also please bear in mind that I have not drawn according to the scale. A depletion region generally when it is fully developed is only 1% or maximum it is 1% of the total diode length, or even less than, very much less than that 1% also. So here I have not drawn this depletion region as per the scale, because I wanted to make a lot of things clear within this depletion region. So please do not go by that scale. If this much is the depletion region, then the diode length is very large. So in this depletion region, as they are leaving behind their immobile or fixed ions, then there is developed an electric field from this side to this side, from positive to negative charge. But we have understood that this depletion region is not suddenly created. It is slowly growing. So therefore the electric field is also growing up slowly. As the depletion region is widening, means as the holes from this side to this side they are diffusing, the electron from this side to this side they are diffusing, then an electric field is also growing up. And then we reach up to a situation when the electric field, which is in opposition to the diffusion process. So let me mention this: the electric field developed is in opposition to the diffusion process. So this is a very important thing. So therefore there will come a steady state, so that no further diffusion will occur. The electric field developed will stop further diffusion process, and the widening of depletion region will stop. And I have assumed in this drawing that this steady state has been reached, so that this much is the final depletion region, which I have already marked from here to here. So this whole process, again please mind it that the electric field developed within the depletion region will be in opposition to the diffusion process. The diffusion process is that free electrons from the n side are diffusing towards the p side, and they are recombining, they are losing their existence. Similarly, the holes from the p side are going towards the n side, crossing the metallurgical junction, and they are diffusing, and they are finding one electron, they are recombining, and they are again losing their life. And while they do so, they are leaving behind the fixed ions. That those fixed ions are creating the electric field from n to p within the depletion region. So this electric field is from n to p within the depletion region only. And please also remember that from basic physics that an electric field is only confined in a region where there is a where there are free charges, or where there are charges. If you see the outside scenario, the bulk scenario, the remaining part of this, or mainly this, is called the bulk region. This is bulk N, this is bulk P. The bulk name is given to that region which remains almost unaffected from the phenomena, from this phenomena of diffusion or drift. So that part which is unaffected, or which is not much influenced, is called the bulk region. So bulk region is mainly towards the end terminals of the diode, but we basically assume that after the depletion region, if we move slowly towards the end of the diode, we will finding the bulk region. So remaining all regions are bulk region. So the electric field can never come out of the depletion region, because in the bulk region there is still a scenario which makes the material neutral. Because if you see any pair of fixed ion to the free carrier is in totality it is a neutral atom. Similarly to this side, if you see a fixed ion with its contributed hole is a neutral atom. So therefore the bulk region, the remaining region other than depletion, is basically neutral in totality. Also, this whole depletion region is also neutral in totality, because the amount of plus q is same as the amount of minus q this side. But if you only be confined towards this side, the depletion region of p side, then it is negatively charged. If you only remain confined within the depletion region of n side, then it is positively charged, as you can see here. So therefore the electric field within the depletion region, which is opposing the diffusion process, remains confined only within the depletion region. It cannot come out of it. So therefore in this scenario, let us understand the so at the steady state, I told you what is happening at a steady state after some sufficient time t2. So at t0 the carriers started diffusing towards each other. At some time t1 they were still diffusing with lesser effect, because the electric field started opposing them. And up to time t2 they have fully diffused, and still they are trying to diffuse, but in opposition to the diffusion process there is existing an electric field within the depletion region which is opposing the further diffusion process. So at a steady state the electric field within this, let me call this Ex, within the depletion region is equal to the diffusion phenomena. Now how to quantify this in mathematics, that we'll see later on, but this is how we understand. So then there will become a fixed width of depletion region, and as you can see this side the width is, let's say, W, because it is P side, so WP, and this side it is WN. Then total depletion width is basically Wn plus Wp. And interestingly, if you see, the depletion widths are not same both the sides. And we expected this because you see in my drawing, in this drawing, it is very clear that in order to get the same amount, same numbers of holes this side, the 8 electrons had to travel much deeper, because this side the concentration was less. So in order to get the same number of free carriers, they have to move to much deeper portion of the P side. So therefore the region which will have less doping concentration will have more extended depletion region, and the side which will have larger concentration will have relatively smaller depletion width. So in this generic profile, in this generic scenario, because as Nd is greater than Na, Nd is to the N side, Na is to the P side, therefore as you can see from the figure, Wp, which is to the P side, is greater than Wn, which is to the N side. So the reverse will happen. And there is a small proof for this also. Let us do this, which is called charge neutrality. Within depletion region. This says that within the depletion region, as we have very clearly understood the recombination process, that the same number of free carriers will get recombined with the same number of carriers to the other side. So plus Q has to be same as minus Q. So let me write it like this: the plus Q side of N has to be same as minus Q side of the P, and total number of carriers, the total amount of charge plus Q to the N side will be the concentration of fixed ion, which is same as the concentration of impurity atoms, Nd, into the volume, because this is per unit volume. So the total charge will be concentration into volume. So the volume to this side is this thickness Wn into the cross-sectional, the width inside, which is not clear from this two-dimensional picture, but the cross-sectional area is same throughout. So therefore I can take it A as a cross-sectional area. So A remains same both the side. So this is volume, this is charge per unit volume, this is concentration per unit volume, and this total Qnd is the positive charge per unit volume. Similarly, this is the total volume, so this is the total charge, and this has to be equal to the charge per unit volume to the depletion side into the volume of this, which will be Wp into cross-sectional area. So if you see area gets cancelled, Q and Q gets cancelled, and Nd by Na is equals to Wp by Wn. So they are in reverse proportionality, means the depletion region of the P side upon the depletion region of the N side is in the reverse proportion, means Nd is the concentration of carriers to the N side upon P side. So this is towards the P side, this is towards the N side, but here this is towards the N side, this is towards the P side. So if the concentration of N side is larger in my example, then the depletion region will be smaller in this case. So that we understood intuitively, and here is the proof of that. So please remember this equation, this will be utilized in a lot of numericals. So we'll save this equation for the future use. And let us come to the further details. So this is the atomic picture or atomic structure scenario of the microscopic understanding of pn-Junction diode. But let us also understand what happens to the energy band diagram or to the Fermi levels. So for that, again I'll have to start with the basic isolated Fermi levels or the energy band diagram. So here I have joined them, but again please go back and understand, when they are not joined, when the metallurgical junction is not formed, then what is the scenario in the isolated. So when things were isolated, then we all know that this is the P side, and in the P side, if this is the intrinsic level, is same to both the sides, because we are assuming, but they are not joined for the energy band diagram. Here I have shown them joined, but here please assume that still both are separated. So this is EI, this is EI to the P side, to the N side, and this is EC side, EB to the valence band level, valence conduction band edge, valence band edge, conduction band edge to the P side, valence band edge to the P side. So because before they are joined, both are of same material, and nothing has happened so far, because we have not yet joined for this picture. For here we have joined, but for this picture we have not yet joined, so nothing much has happened. And let us draw their Fermi levels. We know that for the P side the Fermi level lies below here, so this is EFP, here it is here EFN. So this is the scenario, and we must concentrate on Fermi level, because this is the level which is in direct relation with the carrier concentration, free carrier concentration. So let me correct one small mistake. If you see, I have assumed or basically go to the semiconductor theory. There we know that the distance or separation of Fermi level from the intrinsic, this error or this difference basically gives us the total free carrier concentration. Larger this separation means lower the Fermi level to the P side, more number of free holes are present. Similarly, larger this variation, more this variation, Fermi level to the upper side means more number of electrons, free electrons to the N side. And in my this atomic structure view, I have assumed that the concentration of Nd is more than the concentration or the concentration of acceptor impurity. So let us give some figures. So let's say Nd is 10 to the power 16 and Na is some 10 to the power 15. Though this is a very vast difference of one order, but just to make it simple, let us assume this. So if this side is less number of carrier concentration, then this difference should be smaller as comparison to this. So let me have some. Now it is somehow clear that this difference gives us this. So now still they are isolated. So as soon as we bring them together, we join them at the atomic structure, we have understood there happens a diffusion phenomena, and electric field is also grown up slowly, and very soon we get a steady state like this. So once we get a steady state, there cannot happen a current flow, because we have not connected them in any circuit. So as there cannot be a charge sharing, there cannot be a current flow throughout the metallurgical junction, so the Fermi level have to be aligned throughout the pn-Junction diode. Please remember, this is a very important rule. If there is no charge sharing to two separate regions, then their Fermi level has to be aligned. That the Fermi level difference indicates that there is a charge sharing or there is some current flow. So, but we know as in a steady state, when they are joined, when the depletion region has occurred, there cannot happen a current flow in the open circuit case. So in that case, what will happen? The Fermi level EFN will get aligned with this. So in order to do so, this shifting of or the twisting of the Fermi level or the whole energy band diagram will occur. So what will happen after that? So let us understand this whole band slowly comes down, this whole band slowly goes up, so that these two Fermi levels are aligned, because there cannot happen a charge sharing in the steady state. So at the steady state, while there was happening a diffusion, there were happening a shifting like this, and as soon as the steady state is developed here, the electric field has restricted the further diffusion process. The Fermi level have been aligned completely. So both things are same. Here we understand in the energy band diagram, we understand it in the energy band view or to the energy band view. Here we understand it at the atomic structure view. So at the steady state, the Fermi levels are aligned. So there is a trick that first of all draw a Fermi level which is aligned throughout, then accordingly draw the remaining things. So this side is E, F, E and E, F, N, and the remaining things are E, F, P this side, and because this is P side, so this earlier intrinsic one, here it is, this is the scenario, EVP, EIP, ECP. Similarly, if this is the Fermi level to the N side, then it is closer to the conduction band, and the distance from intrinsic level is much, so that it tells us that the concentration is larger. This is ECN, EIN and EVN. But please remember, because both P and N regions have been derived from the same silicon intrinsic material, so this whole ECN minus EVN has to be same as ECP minus EVP. So if in my drawing they are not equal, then it's my mistake, but they have to be equal because they have been derived from the same intrinsic silicon material. So if this is the depletion region, then there is some phenomena. The bulk portion is intact, but closer to the depletion region, this phenomenon is happening. I have very clearly told you that I have widened depletion region too much to make this diagram very clear to you. Otherwise, this depletion region is not this much up to the scale. So this band bending actually happens in order to align the Fermi levels both the side. So when this happens, this also has to happen. This may not be exactly a straight line, but in order to make some good picture, I'm just drawing it like this. So okay. So you see the bulk region is approximately, this region remains intact. This region remains intact, or there is no much disturbance, whereas the region which is under the influence of depletion, there the band bending has occurred, and that band bending is occurring or happening all because there is a charge variation from N side depletion region to the P side depletion region, but because there is no current sharing process, there is no charge sharing process further, so the Fermi levels have to be aligned. So here you can see this distance is basically the responsible thing for the concentration to the P side, which is approximately Na, and this distance at the bulk here is the responsible for the Nd. Larger the Nd, higher will be the Fermi level, much closer to the ECN. Larger the Na, lower will be the Fermi level, below the EIP. So with this, it is very clearly understood that there is a total potential difference occurring, all because of this energy band bending. So if you see, due to this electric field, or due to this two discrete charge containing regions, there happens to be an electric field, and due to that only the band bending has occurred, and the total band bending is this. Total band bending. So let's say this is delta E. So this delta E is the total electric field from this end to this end. So if I have to so this delta E is the total energy difference from this end to this end, and this energy difference could be converted to the potential difference. So that is delta V by Q is Q delta V, and this delta V is nothing but the potential difference or potential developed across this. See, as the electric field is developed here, this makes a potential difference across it, because there is a fixed charge scenario from plus Q to minus Q, so there has to be a potential difference plus minus delta V. So this delta V is called built-in potential or junction potential, which is acting like a barrier, and it is ensuring that no further diffusion process takes place, or it makes the diffusion process difficult. So until and unless you apply some force on drift, the diffusion process effectively cannot take place, because there has been existed a potential difference, built-in potential, junction potential, potential barrier of delta V. This is in coordination with the electric field. If there is an electric field, there is a potential difference. So this potential difference, very clearly you can see, it can be related with this band bending to delta E, and if you have to calculate this band bending, it is same as this, because EC, EI and EV, they are moving in parallel. So this is basically delta E. Total band bending is Q into delta V, or let us make it more relevant symbol, Q into VBI, built-in potential. So there develops, or there comes a potential difference across the depletion region, which is in accordance with the electric field developed within the depletion region, which is this. And from here, as you can see, this is nothing, this whole value is nothing but EIP minus EFP plus this. So it is this plus this. So this value is EIP minus EFP plus EFN minus EIN. And this equation only gives us the formula for built-in potential. So we can proceed and we can find the formula. So for that we need to go to the chapter number 1, and we should recall that what is the energy band formula for the p side or n side. So from there we know that EIP, so let me call this equation number 1, EIP, or let me call this, yes, sorry, EIP minus EFP is basically KT ln Na by Ni. So you can very clearly see, larger the Na, more will be this distance between them, larger will be this. So EI will remain at the same place, you can imagine it like this, and EF will be moved to the lower side. So the distance of Fermi level below to the intrinsic level tells us that how many more number of holes, free holes, have been created or generated. So this is this relation, and similarly EFN minus EIN is KT ln ND by Ni. This all is from the chapter number 1. So if we So it makes it kT ln Na Nd by Ni square. So the VBI built-in potential is kT by Q, which is Vt. In a shortcut you can write it ln Na Nd by Ni square. So this is very important formula, and this is called, as I'm saying, is called built-in potential or junction potential or potential barrier. It is called built-in potential because it has happened all due to the internal semiconductor phenomena of within the diode. So it has happened within the diode. We have not applied this externally. It has developed itself. So that is VBI. So that is built-in potential. Junction potential because it develops across the junction, metallurgical junction. Potential barrier. It is called barrier because it restricts the further diffusion process, further electron and hole diffusion across the junction until and unless we apply some drift phenomena, we force them to diffuse. So there is one more method to come up to this relation. So let us see. This is one way. Using the energy band diagram, we have proved, we have developed the built-in potential.